In the high-stakes world of Formula One, victory is measured in milliseconds, but safety is measured in millimeters. At the heart of every car lies the monocoque, a French term meaning single shell. This isn't just a frame, it is a rigid, indestructible survival cell designed to protect a driver during a 200 miles per hour impact. Imagine a structure so strong it can support the weight of a double-decker bus, yet light enough for a single person to lift. This engineering marvel is the product of aerospace technology, extreme chemistry, and a baking process that rivals the precision of a diamond laboratory. Hidden within these dark, sleek curves is a complex sandwich of carbon fiber and aluminum honeycomb, engineered to be stiffer than steel but a fraction of its weight. Today, we go inside the clean rooms and the massive industrial pressure cookers to witness how engineers transform soft resin-soaked fabric into the ultimate shield for the world's fastest drivers. This is the story of the F1 monocoque, where physics meets pure survival.
The journey begins with black gold, carbon fiber. But not just any carbon fiber. F1 teams use specialized pre-preg sheets, which are carbon fibers pre-impregnated with a precise amount of epoxy resin. These fibers are incredibly thin, significantly thinner than a human hair, yet they possess a tensile strength that shames industrial-grade steel. These rolls are stored in massive industrial freezers at -20 degrees Celsius, or 0 degrees Fahrenheit. Why? Because at room temperature, the resin begins to cure and harden. To keep the material workable, it must stay frozen until the moment of fabrication. There are different weaves for different needs. Some provide stiffness in one direction, while others are designed to absorb energy during a crash. To build a single monocoque, engineers will use up to 60 different types of carbon fiber mats, each selected for its unique mechanical properties. It's a jigsaw puzzle where the pieces are microscopic and the stakes are life and death. Before a single layer of carbon fiber can be laid, you need a perfect surface. This starts with the pattern. Engineers use massive 5-axis CNC machines to mill a life-sized model of the chassis from a block of high-density epoxy tooling board. The precision here is staggering. We are talking about tolerances of less than 0.1 millimeters. From this master pattern, a female mold is created. This mold is the negative image of the car, and its surface must be as smooth as glass. Any imperfection in the mold, a tiny scratch or a speck of dust, will be transferred directly to the final chassis, potentially compromising its aerodynamic performance or structural integrity. Once the mold is ready, it is polished to a mirror finish and coated with a release agent, making it ready for the layup process. This is the foundation upon which the driver's safety is built. Welcome to the clean room. This is where the magic and the labor happens. Technicians, dressed in surgical-style suits to prevent skin oils or hair from contaminating the carbon, begin the layup process. Using laser projection systems that highlight exactly where each piece of fabric should go, they apply hundreds of individual carbon fiber plies into the mold. This is like high-tech tailoring. Each ply consists of fibers oriented in a specific direction, 0 degrees, 45 degrees, or 90 degrees, to handle the specific loads the car will face under braking, cornering, and acceleration. As each layer is added, a technician uses a small tool to debulk the material, pressing out any trapped air bubbles. A single air pocket, even the size of a grain of rice, could create a weak point that leads to a catastrophic failure at 200 miles per hour. This process takes weeks of continuous, meticulous hand labor.
A monocoque isn't just solid carbon fiber. That would be too heavy. Instead, it's a sandwich. After the first few layers of carbon are laid, engineers insert a core material, usually an aluminum or Nomex honeycomb. Think of this as the corrugated part of a cardboard box, but on an industrial scale. This honeycomb core provides immense structural volume and second moments of area without adding significant weight. It creates a gap between the inner and outer carbon skins, making the structure incredibly resistant to bending and buckling. This is the secret to the monocoque's rigidity. When the car hits a wall, the outer skin takes the initial impact. The honeycomb crushes to absorb the kinetic energy, and the inner skin remains intact to protect the driver. It is a biologically inspired design turned into a high-tech shield. Every millimeter of this sandwich is engineered to maximize the strength-to-weight ratio. Once all the layers and the honeycomb core are in place, the entire assembly is wrapped in a series of breather cloths and then sealed inside a heavy-duty plastic vacuum bag. A series of pumps then suck out every last molecule of air from inside the bag. This creates atmospheric pressure that clamps down on the carbon fiber layers, forcing them together and ensuring they conform perfectly to the mold's geometry. But the vacuum isn't just for shaping, it's also for degassing.
Any moisture or volatiles in the epoxy resin must be removed before the baking process begins. If they aren't, they will turn into steam in the heat, creating internal voids. The chassis is now a tightly compressed green part, ready for the most critical phase of its birth, the autoclave. This is the point of no return. Once the heat is applied, the chemical reaction cannot be stopped. The monocoque is now wheeled into the autoclave, a giant, high-pressure industrial oven. This isn't your kitchen stove. The autoclave will heat the chassis to roughly 180 degrees Celsius, or 350 degrees Fahrenheit, while simultaneously increasing the pressure to nearly 100 pounds per square inch, or about 7 times normal atmospheric pressure. This combination of heat and pressure triggers a chemical cross-linking in the epoxy resin. The liquid resin transforms into a hard, crystalline solid that bonds the carbon fibers together forever. The soak time is critical. The temperature must be raised and lowered in precise increments, or ramps, to prevent the material from warping or cracking due to thermal expansion. For several hours, the monocoque is literally cooked into its final, indestructible form. In this high-pressure environment, the many layers of carbon and honeycomb become one single unified structure. After the autoclave has cooled, the moment of truth arrives, demolding. The vacuum bag is stripped away, and the chassis is carefully pried from its mold. What emerges is a dull, matte black shell, the raw monocoque. But it's not finished yet. It must undergo a series of finishing processes. Any excess resin or flash is trimmed away using ultrasonic cutters or diamond-tipped saws. Technical inserts, threaded metal bobbins for mounting the suspension and engine, are bonded into the structure with high-strength adhesives. Every single one of these inserts must be positioned with sub-millimeter accuracy using laser trackers and coordinate measuring machines, or CMMs. If a suspension pickup point is off by even the width of a human hair, the car's handling will be compromised. The raw carbon is then sanded and polished until it achieves that iconic, shimmering finish we see on the grid. Before this chassis is allowed anywhere near a racetrack, it must survive the FIA's torture tests. This is the most nerve-wracking moment for the engineers. The monocoque is placed in a massive rig where hydraulic rams apply several tons of force to specific points: the nose, the side impact structures, and the roll hoop. We are talking about loads equivalent to several elephants standing on a single point of the car. The chassis must not only survive these loads without breaking, but it must also show minimal deformation. Engineers use specialized sensors and strain gauges to monitor how the carbon fiber is reacting. If the structure groans or cracks, months of work and millions of dollars go down the drain. This ensures that when a car hits the barriers at high speed, the cockpit remains a rigid survival cell, even if the rest of the car is obliterated. The result of this journey, from frozen fabric to high-pressure baking, is the safest structure ever devised for transport. The F1 monocoque is a testament to the power of composite engineering. It is a shell that weighs less than 100 kilograms, or 220 pounds, yet it can withstand the most violent forces in sports. When we see a driver walk away from a horrifying collision, we are seeing the success of the autoclave, the precision of the layup, and the incredible strength of carbon fiber. Every curve and every layer has been calculated, simulated, and baked to perfection. It is more than just a chassis. It is an engineering masterpiece that proves that in the pursuit of speed, there is no compromise on survival. As the car exits the pits and hits 300 kilometers per hour, the driver rests inside a dark, carbon fiber heart built to withstand the impossible. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.